Hi everyone, I'm glad you are interested in learning about why GPUs outpace CPUs. And sometimes in life, it's very important to answer the why questions, even though we all know that GPUs are used for deep learning training because they're faster than CPUs. So hopefully in this tutorial, you will learn a couple of aspects of why GPUs are faster than CPUs. And of course, there are many reasons, but let's just look at one of the reasons. Let's get our hands dirty. Obviously, this is a channel where you learn some aspect of Python coding, so we may as well focus a bit on understanding our GPUs a bit better. Again, if you are a subscriber to my channel, you know that we focus quite a bit on deep learning, machine learning aspects. If you're not a subscriber, please go ahead and hit the subscribe button right now, because obviously you're watching this video definitely tells me that you're interested in the type of content that I create on a regular basis. Okay, while you are hitting that subscribe button, look for the thanks button right next to it if you're feeling extra generous. Okay, let's go ahead and jump into the discussion and not waste a lot of time. I try to make this video, keep this video short. Let's see how short that's going to be. But on the screen, you see specifications for both CPU and GPU. And typically when you look for GPU, you often hear about, okay, what type of RAM do you have, right? 32 GB RAM or 16 GB RAM or whatever, 4 GB RAM and so on. And that is, of course, very important because for deep learning training, you are working with large data sets and you would like to store as much data as possible into your RAM for easy access for further processing, right? So the larger, the better it is. Otherwise, you'll have to work with very small batch sizes and all that kind of stuff. Okay, so that I'm not going to touch that aspect because the amount of RAM, it's kind of pretty much CPU can also offer the same thing. But GPUs are faster for other reasons. RAM is important, but they're faster for other reasons. Again, I definitely recommend you to look at a bunch of videos that NVIDIA has done, for example, on the topic of GPUs, focusing on hardware. So I'm just giving you quick high-level overview, but if you really want to get it down and dirty with all the details, then there are numerous videos on YouTube that you can actually tap into. Okay, first of all, CPUs are designed to handle a wide range of tasks and are the general purpose processors. So CPUs are great. They are great general purpose processors and they're designed to do many, many different things, not just one thing. Whereas we'll get to GPU in a minute, but they have few powerful cores. Like when you look at the specifications, you see 24 cores or so on. They don't have thousands of them. They have few of them. They are very powerful, and they are designed to perform these complex instructions to perform a variety of tasks. But GPUs are designed for parallel processing, and they do have thousands of cores compared to CPUs. Originally, GPUs, I mean, what does it stand for? It stands for graphic processing unit, right? So it was designed for graphics. And what's graphics? Graphics is nothing but when you think of 3D graphics, there are a lot of 3D surfaces that you would like to render. If you're playing a game, you're looking at a scene from one angle, but as the character moves along, you look at the same scene from multiple angles, which means each object that's defined in 3D need to be re-rendered, recalculated from that perspective. What does that basically mean? Like every 3D surface, I believe it's still the case, is represented by tiny triangles. It's actually, you put a whole bunch of tiny triangles together to construct a 3D surface. And when you move around, you're actually solving a whole bunch of equations to actually make sure that the perspective is correct from wherever you're looking at this scene. And also the lighting is another aspect that actually comes into this, like a small triangle, a given unit, which is a small triangle on the surface, what color should it display, and what brightness should it display, and in what angle should it be actually displayed, and all that. Okay, so that basically means the point I'm trying to make here is GPUs are designed to perform parallel processing using thousands of cores, and they're designed to perform repeated calculations, which is nothing but solving these set of equations to tell you exactly how the scene should look like. So it's not doing, okay, fire a PowerPoint or do Python or do C++ or some other topic like the recording software here. It's not trying to do all of these different things. It's trying to do one thing and one thing only. I'm spending a lot of time here because I want to make sure you understand that when you want to perform repeated analysis of a specific type, then GPU is probably the right choice for that type of task. So I guess I spoke ahead of time, but this is the summary there. Performing the same operation on a large set of data concurrently. This is what graphics is. And via CUDA, NVIDIA is making the infrastructure, the computing infrastructure available to us to perform other tasks and not just graphics. That's all it comes down to. So you have a graphics card, and it is designed to do a lot of calculations for graphics purposes, but then CUDA allows us to actually use exactly the same infrastructure for other purposes, primarily deep learning. Well, we are not coding in CUDA. You can if you want. If you know C, C++, you can go code in CUDA and access all that low-level hardware, but via TensorFlow and PyTorch, we are accessing the CUDA indirectly. That actually orchestrates how the parallel processing happens on this GPU processor. Okay, now it's all about the number of cores to perform repeated parallel computation. So if you look at the specifications, in this case, if you look at Intel i9 processor, this is the CPU I'm showing you, the total number of cores, 24 here. Now, if you look at NVIDIA RTX A5000, so this is not really high end, but at the same time, obviously not too cheap, somewhere in the middle. It offers us about 8,192 CUDA cores. So just imagine the sheer number of these tiny cores that are doing the same type of task. And now if I have a good way of parallelizing my computation, for example, deep learning, to throw computation on all of these CUDA cores, great. Now I can actually perform tasks at a much faster pace. This is exactly the reason. Of course, this is just a medium scale. There are much better, like NVIDIA data center actually offers a much better infrastructure for example, large language model training, right? So we're not talking about that. We're talking about the workstation GPU in this specific example. Okay, now let's take it to the next level. First of all, how do we quantify the power of GPU versus CPU? So the exercise we're going to do is basically calculating the flops. And I'm pretty sure most of you are aware of this. If not, flops basically stands for floating point operations per second. How many floating point operations can you perform in a given second? So this is a way of quantifying the power of these processors. So let's use some Python coding to calculate flops for CPU versus GPU, and then come back here and finish off one more slide that I want to show you as a summary. So let's jump into Google Colab. And that's because you will have access to GPU when you go onto Google Colab, although it's not a great GPU, but it gives a good example. It serves as a good example because we have a CPU there and a GPU, right? So we can just do run some calculation and then see how long it takes to perform that calculation and compare CPU versus GPU. Okay, before wasting any time, let's jump onto Google Colab now. And if you don't have access to Google Colab, it's a shame. You should just sign up for a Google account and go ahead and log on to your colab.research.google.com, and you have a Python notebook, and go to runtime, change runtime type, and then select whatever the free GPU is. I'm recording this literally towards the end of January 2024. So whatever hardware that you see here, and also in a second we'll see what hardware we have via our Python code. This all reflects the date of my recording, which is at the end of January 2024. You're probably watching this in the first week of February, because I usually take 2-3 days to, whatever, get this video ready and publish it. Okay, so I selected T4 GPU. And if you pay, you actually do get advanced GPUs there, but I'm okay. For now, let's just compare this versus the standard CPU operations. And now let's go ahead and connect it. And let me clear all outputs in case I have something floating around. Okay, so now I have GPU access. I have a lot of text here about what we are going to do. First thing is we are going to measure the flops by running an algorithm that typically people run. Again, this is something that I picked up even back during my C and C++ days. That was a couple of decades ago. I have been doing Python for the last decade. So this calculation, it's called DAXPY, which is double precision A multiplied by X plus Y, which is basically an equation that you're solving, A multiplied by X plus Y, where you have X and Y as vectors that we'll define in a minute. So we're trying to perform this operation using very large vectors, and then see how long CPU takes, how long GPU takes. But first, before we do anything, let's go ahead and see what type of physical devices we have. What CPU do we have? What GPU do we have? So we have a good understanding of what hardware we're working with. So let's go ahead and run this line. I'm not going to explain every line. It's basically, I'm using the psutil library to get some information about the CPU counts and the frequency and all that. And I'm also printing out the GPU information. And for that, I'm using TensorFlow, so I can actually get some information about my GPU device right there. So upon printing this, so first of all, it says my physical cores is 1, number of cores is 2. It's a dual core processor, as you can see. This is a shame because it's only 2, right? I mean, the Intel i9 processor is much faster. So the comparison that I'm showing you here between the CPU and GPU, please keep this in mind. When you do this on your own workstation where you may have much advanced CPU, then you won't see probably the same humongous difference that you may be seeing right now when comparing CPU and GPU, right? So keep that in mind. It completely relies on your local hardware. So when it comes to GPU, what do we have? We have Tesla T4. This basically means CUDA 7.5 compute capability, and we have a NVIDIA Tesla T4. And the Tesla T4 specifications is, in fact, at the time of the testing, the GPU offered by Colab T4. I put this note because I don't know when you're watching this. So the Tensor cores, NVIDIA CUDA cores, 2,560 cores is what we have in this Tesla T4. And according to the documentation, the single precision performance, which is what we're going to do later on, is 8 teraflops. That's a lot. 8 teraflops. Remember, that's not what you get every time. You have to push the limit to get there, but that is what its maximum performance is. Okay, so with that information, let's go ahead and calculate the flops for CPU and GPU using our DAXPY operation, and there's the function. So basically, if I say, if I call this function by saying, hey, use the GPU as true, obviously we are enabling GPU, otherwise we are setting our device as CPU. This is the best way to actually perform your testing, and here you have your operations, which is my A is just some scalar value. I just put 2.0, you can put whatever value there, it doesn't matter. But when our X and Y's are arrays, a random arrays of whatever the size that you define. It can be 100 by 100 vectors. So we'll control that in a second, but then all we are trying to do is multiplication, scalar multiplied by X plus Y. So this is the operation we are performing, and I'm timing it before and after. So it can calculate the elapsed time and then just return what the time is. That's it. And down here, I'm defining my array size to be 10 to the power of 6. That's a large array. You can try 10 to the 7, 10 to the 8, 10 to the 9, like larger arrays, because the larger the computation, the bigger the difference that you may notice between GPU and CPU. Yeah, because if it's a simple calculation, it doesn't matter what you use. It's for the extra load where GPU really shines. Now, if you try that, the system may crash because obviously you need to hold that in your memory, in your RAM. So depending on what you get, system may crash. 10 to the power of 6 worked last time, so I'm just leaving it over there. Now, CPU flops is basically we are performing our DAXPY with GPU equals to false, and I'm printing that. And the same thing with GPU. Again, if you're running this on your local system, you may as well put this in if else, because if GPU is not available, you should be knowing that, hey, I'm not using GPU, right? So that's why I put this down here. So let's go ahead and run this calculation. That's pretty fast. And you can see my CPU flop. I'm a bit surprised. I was expecting both CPU and GPU to be of the same speed for this calculation, But either way, my CPU flops is 1.35 10 to the 8 per second, right? And GPU is 3.4. I bet if I run this again, it will be much closer. Let's run that again. You see, yeah, this is exactly what I was expecting. Of course, each time you run this, it may change slightly, but usually you get GPU to be slightly faster compared to CPU for this calculation, this specific calculation with 10 to the power of 6. Array size. You may see CPU and GPU to be equal. In fact, you may actually see CPU to be much faster than GPU depending on your local hardware, because this is not an intense calculation. I'm stressing on the fact that this is not an intense calculation because what we really need for deep learning is matrix multiplications, right? There's a lot of matrix multiplication. You're doing convolution operations, for example. You have your image and you have your convolutional kernels, and you're doing a lot of matrix operations there. So this is where I think a true GPU test would be. So I think for modern testing, instead of DAXPY, I would be using this matrix multiplication. And luckily, TensorFlow gives us a very easy way of performing this matrix multiplication. So let's go ahead and use the TensorFlow library for that. And I'm also importing Seaborn for plotting. I'm not sure if I ended up using Seaborn or Matplotlib, but either way, it doesn't matter because I just want to plot the flops, number of flops for the data size. So what am I doing here? Exactly the same structure. Whether the device is GPU or CPU, you define that. And then one thing I'm doing here is to reset the default graph and clear the GPU memory. Did I write a note about it? I thought of writing it. I don't know if I did that. Yeah. So to make sure we start with a common baseline for each matrix multiplication task, because you don't want to perform tasks and then the GPU memory is not released or whatever. I just want to make sure we start from blank slate for each of these calculations, because this is almost a scientific testing we are trying to do here. So we release the GPU memory. We'll disable, in addition to doing that, we also disable the eager execution, because in TensorFlow 2 point whatever, this is enabled by default. And this execution is basically, it makes it runs this immediately. We don't want that. We want to clear the graph and we start from scratch. So that's why I'm disabling that. So that's what you will see here. So if you look at, reset the default graph. So it's resetting this graph, the TensorFlow graph, and then it starts this calculation. And A is, where is it? Sorry, yeah. And A is an NumPy array of matrix size by matrix size. If I define my matrix size as 1000, so this is 1000 by 1000 array. B is 1000 by 1000 array. You can try different matrix sizes, but that's not the point here. And now let's basically say disable the eager execution and then perform our TensorFlow.matrix multiplication of A and B matrices, and then report the final time and calculate the time. And just so we have the final value as teraflops, I'm just dividing this by a terabyte, 1 to the power of 12. So it reports the teraflops instead of just flops. Okay, now what fun is it if you just do it for one specific matrix size? So that's why I'm doing this for 100, 200, 300. It should run pretty fast until about 5,000 probably, and then 7,500 and 10,000 probably will take a minute or so. That's okay, I'll pause the video because it's worth looking at the result. And I'm capturing all the result into, I intend to capture all the result into a data frame. So I'm capturing this into the matrix. I'm capturing the information about matrix size, GPU teraflop, CPU, and then the percent speed up, which is nothing but my GPU speed minus CPU speed divided by GPU speed. So we know how much faster GPU is compared to CPU. That's all I'm trying to see, like 10% faster, 20% faster, and so on. That's it. And now we are just running through the loop, basically getting the GPU and CPU values and calculating how much faster GPU is compared to CPU. So which is again GPU minus CPU or CPU times 100. So it's a relative difference there, and basically storing all of these into the lists that we defined earlier and capturing all of that into a pandas data frame. So let's go ahead and run this. And you can keep an eye on the screen right here. You see how it says minus 98% for GPU, minus 93%, which basically means CPU is faster than GPU, which is no surprise for very small data sets. yeah, why do you need GPU? CPU is faster. It has the required memory, it has the required speed, and it has the required bandwidth to perform these type of operations. But as it goes by, as the matrix size increases in this case, you see as you go to 300, now GPU is 95% faster than CPU already. And now for size 400, it's 267% faster. And as you can see, the story here, it's getting faster and faster. Well, it went down here from 900 to 1000. That's, again, stochastic. That's just statistical variation. You run this another time, you probably get this slightly lower than this, but it doesn't matter. Let's plot this and look at the trend in general. As I guessed earlier, it's now performing 7500, and I'll give it a minute for it to finish the 10,000 matrix size. If I bump it up, I think I will run out of memory here and it will crash on your local system. It may run, assuming you have much better system than what Colab actually provides. But for small matrices, for small sizes like 100 by 100, 200 by 200, the computational advantage that the GPU is giving us, it outweighs the overhead and the warm-up type and a lot of things. You know, there is a overhead, but if you're just doing one little calculation, you don't have that advantage, right? I mean, if you have a lot of calculations, that's exactly when GPU's advantage actually shines. Okay, so I have been talking a lot, so let's wait for that operation to be done and go ahead and plot it so we can visually see what we have seen in numbers over there. Okay, so it's finally done. I waited 30 more seconds, I guess. And let's go ahead, and you can see the GPU for 10,000 is 4,500% faster than CPU in terms of number of, teraflops right there. You can see the numbers right here. Anyway, let's plot and have a quick look at it. And let's see. So we are plotting all these, and where is it? Oh, there you go. Oh God, let me decrease the size. I increased the size so the text is visible for you, but now it's ridiculously large. So, okay, one more time. There you go. Okay, so here the green line indicates the teraflops for these calculations using CPU. So it's kind of saturated, you know, it's doing its thing at its own pace. It's not getting any faster as you get more and more, or as you provide more and more data. But as you can see, the GPU teraflops, the blue line, is going up, and red line should follow, obviously, because we are seeing how much faster the blue line is compared to the green line, which is basically the red line that you are seeing here. So it's almost exponential. So as the data size actually, or the calculation size go up, the speed advantage that you gain from your GPU scales, not just in a linear way, but what seems to be here in an exponential way. Again, I have no scientific proof to say that it's exactly exponential, but you can see that it's definitely not linear. It's definitely faster than linear. In this case, visually, it looks like it's exponential right there. Okay. So what did we learn from this experiment? We learned that GPU is highly effective in handling larger and more computationally intensive tasks, right? So on the other hand, CPU appears to plateau. Now, after all this exercise, I'm going to say something like, forget the flops. It's all about the memory bandwidth. Well, I shouldn't say forget the flops in general, but flops is important, just like RAM when it comes to your GPU memory. Or VRAM, I should say, but it's all about memory bandwidth. And let's understand this. Again, let me jump back to the PowerPoint slide because it's easy to read over there. So just give me a second. And this is where we stopped earlier. So let's continue this. So basically, memory bandwidth, which is something that you see in the specifications, both for your CPU and also GPU, it's nothing but a measure of how quickly the data can be transferred between the processor and the memory, right? You have lots of memory, great. And you have your processor with many cores and everything, awesome. But these two need to communicate. You need data transfer between these two. And it's very important for this to be very fast, right? And High bandwidth, of course, is very important for tasks that include frequent access to large data sets. That's why for CPU, it's not that big of a deal to have a large memory bandwidth. It's always useful to have it, but for CPU, it's not of a high requirement because you're working on versatile tasks, and really speed is not as important as it is for GPU type of tasks. You're playing a game and your graphics card, you need the scene to be, updated right away. You're doing your TensorFlow calculations or, your tensor calculations. That needs to be pretty fast, and the data needs to be moved between your memory and your processing unit as fast as possible. So again, for deep learning, this is absolutely perfect. And also memory bandwidth becomes very, very, very important, in particular when dealing with large matrices, very large matrices, because transferring between the processor and the memory needs to be very efficient right there. So this is why when you look at the specifications, of course, I kind of put a rectangle around this number of CUDA cores, which helps us in faster flops, but also look at memory bandwidth. In this case, it says 768 gigabytes. It can transfer 768 gigabytes. That's 3/4 of a terabyte, right? So that's an incredible amount of data per second. But when you look at the memory bandwidth of a CPU, in this case Intel i9 chip, which I think is state of the art as of today, it says almost 90 gigabits per second. Not bad, but of course, if you are working with massive amounts of data, this is exactly what you need to be looking for. So in summary, why is GPU faster than CPU? Well, first of all, it's faster, like at performing the floating point operations per second, so it can do much more. The larger the data, the faster or the better the advantages of GPU compared to CPU. For small data sets, it doesn't matter. Don't worry if you have GPU or CPU. For small data, if you're trying to come up with a train a model on the digits data set, for classification, CPU is more than enough for you, okay? But very large data sets where you're trying to train these large language models, the better, options would be GPU, obviously, with a lot of CUDA cores. So you get a lot of calculations done in parallel, but also memory bandwidth is very, very useful. I have to compare memory bandwidth between A5000 and some of the other ones, because we just looked at T100 that Colab gave us. It's much less than this. I think it was around 200, right? Gigabits per second. So this is another aspect or reason why your calculations are much faster, or why your training is much faster on GPU. Okay, I hope you really found this tutorial to be useful. This is really not a typical tutorial that I do like Python coding to perform certain tasks, but like I mentioned, the why questions can be very important to answer sometimes, because that really enlightens you in terms of why certain thing is the way it is. So if you like these type of videos, again, let me know as usual by commenting down below in the video. But until then, guys, keep learning. Hit the subscribe button, and let's meet again in the next tutorial. Thank you.